Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we're going to take a look on the design capabilities of robots when designing reinforced concrete columns. So to do that, I'm going to select my 2D frame design and define me a quick frame. This frame is going to be a very simple frame. There is more details about a full structure in the future, but for now, I'm going to define me a very simple frame that is 9 meters in width, and my columns are basically 4 meters in height. I'll apply that. And now I'll just basically draw me some frames. Now, I highly advise you to double check your design codes, and this has been done before. There is a video linked above about checking your codes and preferences. Furthermore, there was a previous video about drawing members and drawing lines. I also highly recommend you to double check this. And there are some other videos on this channel that might be of benefit for you, so also please double check those, and if you like them, maybe you can subscribe to the channel. Alright, so to start with, I'm going to have a reinforced concrete column, and this column is going to be 350 by 700. I'll add that and draw it. One column like this and another column like this. Now for the beam, I'm going to select RC beam. I'm going to define my cross section. Now the cross section, the beam should be the same width like the column, because I'm going to design me a frame and it has to do with reinforcement detailing. Of course, you can choose anything you want, but then you will suffer in the reinforcement detailing section. So I'll just say that my beam is also 350 by 800. I'll just add that, close, and then basically draw it from here to here. Now, a very important topic I need to mention here is that the ASI code stipulates a reduction in the moment of inertia for the beams and columns if you are designing a frame action. So to do that, I'll first of all click on this bar, which is my beam, and go to the section. I remember my section being 350 by 800, so I double click on that and tell him, well, let's reduce the moment of inertia main axis, which is the y-axis, because the y-axis is the axis around which the in-plane moments are applied, and well, this is the y-axis, so I'll just reduce it. You can actually reduce all the inertias if you want, but ASI code asks you for the frame action inertia to be reduced. Also, for columns, the ASI code asks you to reduce the moment of inertia for columns by 30%, meaning that you have only 70% remaining, just to be a little bit more accurate. Alright, fantastic. So everything seems to be fine. Now I need to basically apply me some loads and some reactions. So I'll just say that my frame is pinned in both points here, and I'll just define me some cases. Now please double check previous videos because there is a lot of information in those. I'm just skipping. I'm trying to be very fast here to be concise, so you should check the previous videos. So I'll just define me some load cases like this, finish that, and apply me some loads. Now I'm assuming that the frame spacing is 6 meters and that the load on the slab is 8 kilonewton per meter square, so 8 by 6 is 48, which means that in the dead load I have 48. Of course, I need to double check that I am on my dead load. So I'm applying 48 on my dead load, which I'll just add and click on the beam, and I will go to my live load and add me my live load. Let's say it's 3 kilonewtons per meter square multiplied by the tributary width of 6 means that I have 18 kilonewton per meter applied on the frame. I could add a wind load case, but I'm not, because my point here is not to add wind loads and dead loads and stuff like that. My point is to show you how robot designs columns and how robot provides you with the required reinforcement and provided reinforcement. So I run the analysis. Everything seems to be fine. Of course, I'm going to double check the deflection shape. Yep, it's exactly as I'm expecting to be. Single curvature column, single curvature beam, 90 degrees between them. I once again click on the results, diagrams for members, and I hope that my moment Y looks exactly as I want. Yes, everything seems to be fine. FZ, perfect. Everything is in working order. Alright, so now I'm ready. I can actually ask the robot to give me the provided reinforcement or the required reinforcement. Now, if you click on everything like this and go to design required reinforcement, robot is going to calculate the required reinforcement for all those members. You have beams and you have columns in those members. Now, the members are all, and if you click on ULS, you cannot select anything because you have no ultimate limit state. You have no cases, which means that you can actually not calculate immediately. Now, to fix that, you can either define your own ULS combinations or ask robot to do it automatically. I'm going to define it myself. So I'll go to Loads, Manual Combination. I'll call it ULS. I'll add those two cases, 1.2 dead, 1.6 live, according to the ASI code. I will run my analysis again. select my combination, double check very quickly if everything is right. So I just go to my diagrams for members, click on MY, take a look, normalize basically. Yeah, it makes sense. Check my deflection. Of course, the scale is of the roof, but I mean, it still makes sense. All right, so I'm ready now. So using my combination that I've defined here, I can actually let the Autodesk Robot design me the column and beam by basically selecting them all, going to design and going, of course, I need to calculate my structure by selecting all the elements, going to design, saying required reinforcement for reinforced concrete beams or columns. Now all the members are going to be designed. My ultimate limit state is going to be case number 3 because my combination is case number 3. So I just click like this. Now if you don't apply this and click calculate, you will get an error because you didn't select anything. So you need to select your ultimate state to be your case number 3. You calculate like this, and now the robot calculates for you the members, and you see that the results are correct. Now those are 3 members. One of them is a beam, and you can see that the beam is designed separately. And there is also a column because you have 2 columns. Each column is designed separately. Now in the beam, there is top and bottom reinforcement because beam. And in column, there is no top and bottom reinforcement because it's a column. And columns are usually reinforced symmetrically. Autodesk Robot has an amazing detailer that allows you to detail beams and columns in an amazing fashion. Of course, this was explained in a previous video for beams, linked above. Now in this video, I'm going to explain it for columns. So to do that, I'll basically select my column because that is the goal of my video. I select this column, for example, go to design, and select provided reinforcement of reinforced concrete elements. This will import the column into the column designer, and I'm going to import only my cases here because I want robot to do the casing itself. So you can see that my column got imported, and you can see that the dimensions of the column are here, and the dimensions of the beam are given, and the height of the column, everything is perfect. All right. So of course, now if you click here, you have only one column. You can see the column results, but there are absolutely no results because it didn't calculate anything. So you can now do a blind calculation just to get a feeling of what is happening. Now it seems that the blind calculation worked, and I can actually even export my column, which is amazing, like there was no error. But still, let's take a look on what is happening. So just give me a second, I'll just modify this here. And it seems that my column worked perfectly fine. I'm surprised, I thought that I would get some errors. So, well, if you run the analysis once again, you see that there is no problem and everything seems to be fine. Now, what did happen? When you ran the calculation, the software Autodesk Robot drew the interaction diagram for you for this column and applied all the load cases and decided that a certain amount of reinforcement was required to withstand the applied forces and moment. Now, this is a 3-dimensional interaction diagram. Now, if you remember from your design books in university, you usually had a 2-dimensional interaction diagram because you had a column under uniaxial bending. Now, robot uses the general case in which you have a column under biaxial bending, and you can see that the MY axis has a much larger width than the MZ axis because the MY axis is the main axis or the strong axis of the column, whereas the MZ axis is the secondary or the minor or the weak axis of the column, which makes sense. And you can see that my force values are inside the interaction diagram, which means that the column can carry all the loads that are applied to it. Now you can see there is a multitude of possible combinations that Autodesk Robot checks for you, as well as showing for you that for a certain case, the compression block is just this part of the entire column. Now, for the column reinforcement, you can see that the column has been reinforced according to what robot suggests for you, 6 bars of phi 29, which might be large, but I will show you how you can modify those reinforcements in this video. And for the column note, you can see that the calculation note is produced and everything seems to be fine. Of course, what I like usually is to see also the material survey because it helps me when I start buying stuff for buying materials for my column, because you can see each diameter, how many pieces and what the length is of each diameter. All right, fantastic. Now, I don't like this a lot because, I mean, yeah, I can see that the stirrups are increased near the support, which makes sense because you have shear there. But I still somehow don't like that my bars are 29 millimeters diameter. Maybe I want them to be smaller. So how can I do that? Now you can see most of the points here are similar, and there are some differences. Now those points, the first, second, and third, are similar to the beam provided reinforcement. So please refer to the video linked above for more details about this. I'll just go to my points of interest. My first point of interest is my reinforced calculation options. In my concrete, I want to select concrete like 6 or something, which is 40 megapascals almost. And I want in my longitudinal reinforcement to use phi 16 only. And in my transversal reinforcement, I want the grade to be 420. I hit OK, run the analysis again. Now maybe it will not work, but I think it will. So it did work, and you can see that my column results are still okay-ish, and it's using now phi 16 millimeters for the reinforcement. So that's the first thing I want to talk about. The second thing I want to talk about is, if you go to reinforcement pattern, things change a little bit because you are now in columns. Now you can, for the future, you can actually select corner bars that are different than the intermediate bars, but for me, I will leave those settings are more than enough for me. For transversal bars, in the options, it's allowed for a robot to actually increase the number of stirrups near the support. You can change those settings if you want, and for example, unify all the spacings in the entire column if you wish to do so. And for dowels, well, if you have multiple stories, which will be done in a different video, then there are dowel bars that are going to apply. And for shapes, of course, you can select the shapes of the main bar. I mean, I can just show you if I want to just try something very strange, and I just do that, then you will get reinforcement that absolutely don't make any sense because you have bent your reinforcement. This is never the case, but I mean, yeah, you see that you can do funny stuff here. I'll just keep it as straight, and yeah, well, I think that is what I wanted to do. Now, the final thing I wanted to talk about is the stirrups. Now, ACI code asks you to confine your longitudinal bars to stirrups, and there is a very good code requirement for this that says that if you have bars, you are allowed to have one bar being confined with the corner of a stirrup and one bar not, one bar confined, one bar not, one bar confined, one bar not. You can see that the column fulfills this requirement, and if your spacing between the bars is I think more than 20 centimeters or 200 millimeters, then all of those need to be confined. So yeah, you have more options here, which is basically the column geometry. You can change the column geometry if you want. I don't want to do that. And finally, you have the buckling length, and this is for calculating the K factor and determining if the column is long or short. And yes, ladies and gentlemen, Autodesk Robot determines if the column is long and short, and allow me to show you this in the calculation note. You see that it calculates the KLU over R factor, makes sure that you are not long. So for example here, KLU over R is 19.79, less than 34, so you are short. And it even mentions to you the code equation used, which is ASI code 6.2.5 B and C. So it actually provides you with long versus short check. Now there is a K, and K is 1. But that is not the case, because K is calculated based on the stiffness of both column and beam, and is calculated by the alignment charts. So that's the last point I want to cover right now, which is the calculation of the K factor. Now in direction Z, there is nothing happening because you are dealing with a two-dimensional frame, but in direction Y, there is everything happening. Now first of all, those K factors are calculated from an alignment chart, which is a different one for sway and non-sway. So you need to know what kind of frame you have. Let's say we have a non-sway frame. K is given as 1, and you can see here that you have a pencil, which means that this K is user input. If you click on that, you can let robot do it automatically from the structure. I mean, for example, let me show you. If I click on this case, like 1, 2, 3, with a pinned support on the bottom, our robot asks you now to input your sections for each one of the elements that are connected to the column. So for example here, you have your column, which is member number 2, which is your column basically, 350 by 700. Member number 3 was on the right side, which is my beam. On top of it, there is nothing. So if you give it the member number 2 and member number 3, it calculates the psi A and psi B from the equations of ACI, and then goes to its alignment charts and gives you the buckling length, which is 0.95. Now you can assume 1 for conservativeness, but 0.95 is perfectly fine. Please notice that the moment of inertia here is the reduced moment of inertia, because I asked robot to reduce the inertia of beams by 2.35 and of columns 2.7. You can see that there is a reduction factor here, and this is extremely important to include because ACI asks you to include those reduction factors on those elements before you go to your alignment charts. Because you see here you have your reduced moment of inertia, which is used to calculate your K factor. One final point that I want to mention here is you notice that the beams have a larger reduction factor than the columns. The reason behind that is that beams are usually under pure bending, so almost half of their section are under tension. So there is, and concrete cracks under tension, so it makes sense to reduce the inertia. Whereas columns are usually under compression, so there is not much cracking happening in the section, and that's why you are allowed to use more inertia for columns. All right, so you can either input it yourself or you can let robot calculate it for you. And now I changed something, so I need to recalculate my column. I just do that very quickly. And you can see once again the note that everything seems to be fine. And that's it. That's all what I wanted to talk about in the design of reinforced concrete columns, be it required reinforcement or provided reinforcement. I hope that this video was enjoyable for you and that you have learned a lot. If you enjoyed this video and liked it, please share, like, subscribe, and comment. Especially subscribe because it helps a lot and increases my reach. Now, once again, this video might be underwhelming because of the mediocre amount of complexity in it, but this serves as an introduction for future videos where I will be designing and modeling full structures. So stay tuned for the good stuff that will come in the future. Anyway, this is the Civil Engineering Essentials channel, and we will catch you in the next video.